In this discussion video, we'll do an example where we have to switch an integral from a dx integral to a dy integral to be able to evaluate it. So this question says evaluate the integral from 0 to 1 of arctan of x dx. So this isn't a function that I know how to take the antiderivative of, at least not yet. We need a technique called integration by parts to actually do the antiderivative, which we won't talk about in our class. This typically we cover in Calculus 2, which at Berkeley is Math 1B. So there's got to be some other way for us to do this. So let's draw a picture of this function. So I'm going to draw some axes. So remember, the graph of arctan looks like something like this, goes like that, and it has these two horizontal asymptotes. It's got a horizontal asymptote down here and one up here. And the one up here is at positive pi over 2, and the one down here is at negative pi over 2. But this is y equals arctan of x. So this integral represents the area under this curve over the interval from 0 to 1. So here's 0, 1 is going to be somewhere here. So we are talking about this region. So this region over here. Okay, so if you were to take 1 and plug it into arctan, arctan of 1, if you work it out, is pi over 4. So my idea here is, because I can't do this antiderivative directly, to find this area, what if we used a dy integral? What if we thought about this in terms of the right function and the left function? So remember, our area between two curves using a dy integral is you get the integral from some number c to some number d of x sub right, your right function, minus x sub left, your left function. And this is going to be a dy integral, because you'll isolate the x's in the equations, so x sub right will be some formula in terms of y. Same thing with x sub left. Okay, so if I look at my region, I have to draw, the way I figure out my right function and my left function, if I'm not sure, is I could draw some horizontal lines. So if I draw any horizontal line in this region, maybe one down here, maybe one up here, the right function is always along this vertical line where x equals 1, and the left function is on the graph of arctan. The issue is, on the graph of arctan, I need to know what x equals so I can plug in for x left. Right now I know what y equals. Okay, so if we have y equals, let me rewrite arctan as tangent inverse of x. We can transform this to write it in terms of the original function, tangent. So in terms of tangent, it'll switch the input and the output. So now the y will be the output and the x will be, sorry, what I mean to say is, so right now the y was the output, that'll get plugged in to tangent, and the x was the input of tangent inverse, that will now be the, output of tangent. Okay, so now I know what the equation of this curve is with x isolated. This is equivalent to writing x equals tangent of y. Okay, so I get the integral. The smallest value of y here is 0. The biggest value of y is pi over 4. X sub right is just x equals 1. And then minus my x sub left is tangent of y. So I get tangent of y dy. Okay, so from here we're ready to do the antiderivative. So for the 1, that's going to be an easy antiderivative. That antiderivative is just 1. For tangent of y, we have to rewrite tangent as sine over cosine. And we've actually done this before in a previous video. From here, we would want to do a u sub. Okay, but we've done that in a previous video, so I'm not going to do it again. From here, I want to leave this as an exercise for you to work this out. So I'll put a dot, dot, dot. So that I'm going to leave for you. But if you work it out, it'll turn out you end up with pi over 4 for the integral of the 1 when you do it from 0 to pi over 4. And then the tangent y portion will end up being minus 1/4 ln of 4. And that's our area. So this problem of having an integral represent some area that I can't do directly, maybe because just I don't know how to do an antiderivative, and then I have to approach it in a different direction like I did here. instead of a dx integral as a dy integral, this will show up again in Math 53 in Berkeley, which is multivariable calculus.